Anyway, so what did we do, or what's the goal in reinforcement learning? So we're going to play some games, or we're going to interact with the environment, and it's going to create like a sequence of rewards. And like this kind of sequence of action, state, reward is known as the trace of an episode. Like when we play one round of the game, it's called an episode. And the sequence of state, action, reward is like the trace of the one. And what are we trying to do? For every position we are, in every state we are, we want to maximize all future rewards. We want to maximize all future rewards, which we're going to expect soon, right? And this is this GT here on the slide. And furthermore, we don't want to be too greedy, right? So we say, okay, we kind of discount future rewards because there's some uncertainty associated with future rewards, so we don't want to value them or weight them in the same way we do like the immediate rewards. And the way this discounting happens is like we have some kind of gamma, and we just multiply it with the future reward. And if it's like 2, we just get gamma squared, and then if you have 10 positions we are away, it's gamma to the power of 10. So you see it's kind of very shrinking kind of correction. And this as well is like recursive, right? So say G of t is like all the sum up, which is like the next one plus gamma of all the previous one. But it's not nothing than the reward of the next step plus all the future rewards from the next step times gamma. So this is also again recursive.
What is gamma again? Like
it's a discount, future discount factor. And most of the time it's like 0.9 between 0.99. I see often. So it's kind of like you have your reward, and your future reward you just discounted it.
I'm sorry. Can you repeat the concept of it? Like I don't understand how's that. Like how's it being applied?
So when you calculate the reward, your expected reward of a state is the reward of your current reward, your needed reward, plus gamma of the reward of the next state, plus gamma of the reward of the next state. Say you play a game, you play a whole game. You have all your sequences, all your actions you did, and all your states, and all your rewards for every step. And you say the total reward, or the expected total future reward of a state, you discount the future rewards.
Is it kind of like a net present value? A net present value, like bringing like a future value to present value, kind of like
yeah.
so like a million years in the future doesn't matter as much, right?
Yeah, exactly. So you put some more weight on your current immediate reward, and you kind of discount the future reward. Say you play a game, right? You look at the whole game, you play 100 steps, right? And at the very end, you win the game, right? You get like 1,000,000 points, right? And then if you say, okay, you don't discount the future, then the reward of all your actions is going to be 1,000,000, right? You wouldn't really know which action actually led to the immediate, like you winning, right? So the final reward is going to override all the other rewards. So what you want to do is you want to know which action is going to give you the reward. Yeah.
So is this like you're trying to value
It also seems like
this trace versus
right?
an alternative
In the future.
trace,
This is like something
as opposed to
happening right
the
now.
very next
We're gonna
action?
read together for like 10 steps.
So what you want to do is kind of understand which actions matters in a sequence of matches, right? So that's it.
It's basically how much significance do you give to immediate reward versus future rewards,
Yeah.
in a way.
It's like if I offered you $100 today or $100 in a month, what would you prefer?
Yeah.
Because you can have $100 now and buy chocolate or whatever.
It's the same principle in finance, right?
Yeah.
You multiply e to the power minus RT every time you go to this state. Yeah.
So I'm gonna talk a bit about state. So as noted, like the K-arm bandit was state free, or the reward was independent from your state. And this is like a simple game where you have a state. So you have the state A, you have the state B, right? and then each of the arrows, each of the points here in the image, these small black circles, they are your actions, right? So in state A, you can do action 1 and 2, and in state B, you can also do action 1 and 2. So if you state A, you do action 1, you get 10 points with 100% probability, right? And then if you say in state A, you can do action 2, and with 80% probability, you go to state B, and you lose 10 points. Or with 20% probability, you go back to state A, and you lose 10 points as well. And in state B, you can select action 1. You get with 80% probability, you get 40 points, and with 20% probability, you get 40 points, and you go back to state B. And if you are in state, you just select action 2, state B with 20%, you get 20 points, you go back to B, and with 80%, you get 20 points, it goes back to A. So let's play. You want to play a little bit? So we start in A. So which action would you do?
2.
2. And back in A?
1.
1. Back in A?
Oh, you have to go
2.
2. You're in B? You are at minus 10 points now?
1.
1. You got
1.
plus 30. Plus 50. Plus 70.
Oh, 2.
2.
1.
1.
It's always good to have 1, right?
It's always 2 and 1 alternating. So when you're in state A, you select 2, and when you're in state B, you select 1.
So at this point, does the model will ever choose action 2 from B?
You have you do an epsilon greedy selection, right? So with a certain at the beginning, the model doesn't know. It's gonna wait. There's 2 Q, we're gonna have a state action Q value function, right? And it's gonna gives 1 and 2 the same amount of expected return because it doesn't know. And then it will just randomly select, right? And then once it has finds out, 1 is the better selection, it will just always select 1 until you have the epsilon greedy part, right? So with epsilon probability, it's gonna select 2. So the state is how the environment communicates with your agent. So it tells you which is your current situation which you are in, and it also tells you the next state, current and next state. And we try to maximize our score, and we want to evaluate our score based on the states. And the reinforcement learning algorithm aims to find favorable states and avoid bad states. And it is, in formal sense, a Markov decision process. You have a sequence of actions and rewards, and there is and you have to think about, there's a trade-off between immediate and delayed rewards. Like, say we discount future rewards, so you want to not only care about immediate rewards and don't care about the future rewards, you also don't want only care about the future rewards and not about the immediate rewards. And there's 2 ways we can evaluate the state. So we say we evaluate the state action pair function. So this is QSA, we evaluate the value function for the state and action, and we want to evaluate the state. For the difference between those 2 is, for the first one, both state and action are fixed. So it's going to just take these 2 into consideration. Whereas the later one, you are in a state and you have to think about all your possible actions, and then all the possible next states as well. And this is a Markov decision process, and has one of the beautiful characteristics of a Markov's process. And basically, all your possible future rewards only depends on your immediate and preceding state. So what you have done in all your previous states is not relevant, speaking, for all your future rewards you can make in the future. And the kind of way to interpret this is a restriction on states. So we say the current state includes all the information about all the aspects of both the past and general environment interaction. This makes a difference. So your current state kind of includes all the information you need to make all the prediction about the future. So another way to say it, like the probability of your next state and reward giving a state and action is just the probability of the previous state action given the state and action. And there are two ways to look at this, like the value function. We say a value function of.
Sorry, could you go to the previous one? Could you just explain it again, please? Just this one, yeah. This one I understand S prime basically would be the next state, that is it?
Yeah, so you say, I want to say the probability of my next state and reward given a state of action only depends, so the next state and the next reward only depends on the previous state and the previous
action.
If
I understand this correctly, saying the probability for the next state is dependent upon the reward that I get for a specific state and a specific action?
No, the reward, like the probability that you get the next state and the reward depends on the previous state and the previous action. This is what it says.
Just one step back. Just one step.
One step back. Yes. And the way you can think about it is kind of like the current state should contain or decode all the information you need for inferring your future reward.
So effectively, what we're saying is that S prime and S can also be the same, or would they need to be necessarily different? Would S prime and S be necessarily different? Like last time in the game we went from A, we could have gone back to A also, right? So would S prime also be A again?
But the reward we get doesn't depend on the say we are in A, right? And we select 1, right?
And we go back to A.
We go back to A. So the probability of selecting, like being in A, when you select 1, doesn't depend if you were in B before or you were in A before or whatever, right? It just depends on your current state that you are in A.
So in new memory again. So
there's no memory here for estimating these Q functions. But for the reinforcement learning and for the deep reinforcement learning, there is some memory. But it's more like for generating the training data. It's not really for evaluating these Q functions.
Doesn't matter.
So all previous steps are stored in the memory of the previous step, right? A previous action.
It's more like the current information, the current state decodes all the information you need to infer the next reward. It's not like that this state contains all the information of all the previous states.
If they imagine the state diagram,
So I guess to rephrase this question, the state doesn't have to include everything, but if you want to implement epsilon greedy with this framework, could you do it, or it's not possible because of the way you define Mark? You could encode S to have this cube and N, right?
Say this. I think this is like, epsilon greedy, like the algorithm we used, kind of takes this into account. Well, epsilon greedy, I showed you, it didn't have any information about states. So you can do. So the next algorithm we're going to talk about is going to be dynamic programming. It's going to show you how to evaluate these like Q functions.
So here, I'm not sure if this is going to happen, but so here the future step only depends on the immediate previous step. That's all that matters.
It doesn't matter where you have gone before.
It's a Markov process.
What matters is like where you are right now and what you're doing.
It's this state.
The next state depends, like the next state depends on the previous state, not where you are right now.
No, the future state, the probability of
future state only depends on your current state.
Your current state.
Doesn't matter, like your previous states are not important.
Yeah. You forget. It's a Markov process.
Yeah, you forget everything. What you care is like where I am right now and what I'm doing, which action.
So just like if you go back to that state diagram, if you don't mind. So it's literally, if we're given it, like, for example, A right now, it just looks at the word and the probability, and that's it, of A.
You have to think about it this way, right? It says your next state and your reward, right? So you are 1 and you go back to A. So this is your next state and reward. And depends only on your action and the previous state, right? And the previous state was A, right? So we selected A, 1, right? So say you select B, then the next state would be 1, you go to A. So this is your next state, and your reward would be plus 40, right? And it only depends that you were in B. Doesn't matter if you were in A before that.
Okay. It doesn't matter how you came to be.
It doesn't matter how you came to be.
Okay.
So the only reason why it gets to B is because of the random input. Yeah, it's that it gets, because if its previous state was A and kept choosing A over and over and over again, it would never get out of that loop until you knock it off course with the random.
I will go out of the loop because we do some epsilon greedy thing, right? Where it selects random decisions at certain intervals.
Because it also takes into consideration the action that you take in that space, right?
Yeah, you take.
If you take a different action, you will get a different equation for that.
So, for example, if I'm at A right now, right, and my next state is depending on the action I'm taking, right? So, for example, if I take 2, there's 2 potential.
Yeah.
Yes.
So, which reward is it gonna go with? Which reward am I which reward is it gonna be chosen at that point?
I'm gonna talk about it.
Oh, okay.
So,
Okay.
in dynamic programming, algorithm takes your expected reward and the probability of that state. That takes these things into account. And those, just to let you know, these two are switched by accident. So this is the state function and a random policy, and this is the state action value function. So say we are at a, we want to estimate the future returns of a given state, right? We are in a certain state, and we want to estimate what are our expected returns, like future returns. This is GT. And we say, okay, this is the expected returns under the policy. Like we have some type of policy, like say epsilon greedy policy, or we have like a fixed policy where it says I have to do this action at this state, right? You just randomly initialize. You say you have a grid world, or you have some environment where you have a fixed set of states, you just initialize a random policy for each, like a random action for each state. Then you have like a random discrete policy. And you say it's nothing then, okay, for all the future rewards given the state.
Aren't these two reversed?
Reversed?
Meaning that the value function is below and the action function.
Yeah, they are reversed. Yes. So they're switched. This is the value function for a state, and this is the value function for a state action pair. Yes. And here we say, okay, and the only difference is like, what are my expected given, right? Here we say, oh, my future returns given the state, and you say, okay, for the state value function, we have this my expected returns given a state and an action. And so this allows you to kind of estimate the Bellman equation. So I have an appendix on the slides. You can go to the very end. There's like a more detailed explanation how you get to the Bellman equation. But in the end, it says, okay, I have a value function of a state. And we see we're going to sum over all the actions and over all the possible future states. You see, so we have all the actions and state pairs, right? And we take the reward plus the discounted reward of the future expected state. So this is a value function on the state. And we say the value of the current state is just like my reward of the state I have, and some kind of probability weighted reward of my expected reward, like of the expected value of the future states, right? And we weighted like, this is the probability of performing a certain action in a state given a policy. If I have a discrete policy, of course, then the probability is going to be 0 for all the other actions, and for one action is going to be 100%. And this is the probability. This is what you saw in the graph with the arrows. This is the probability of observing the next state and getting a reward, giving a state in action. So we are in A, we say, oh, we select an action A, and then it's going to give you 2 possible rewards and 2 possible future states, right? So this is this part here. And this is just the probability in our policy of selecting a certain action. So there's a little bit more visual explanation of this thing. Say we are here, this is our state, right? This is our current state. And we have 2 actions, right? And these are discrete actions now. So we do this action, we always have the same outcome. It's not like the diagram with the circles, the graph. Unfortunately, yeah, this was originally animated. I could have asked you what is better. So we have we take this action and then we say, okay, we will move the same amount of frames ahead. And we reward our agent for the frames we move ahead. And we see here in both states, we are the equal amount of frames ahead. So they get the same reward. But we are estimating the value of the state under a given policy. So actually, the first one is better, because the value function of the next states, this one is a better, way better state than this state, because here in the next frame you're going to die, you lose a lot of points. So the value function of my current state depends on the value function of my next states. And this is the idea behind the value function. I try to move to favorable states. I don't really want to make immediate reward, but I want to move my agent in a strategic way. Yes?
How further do we look at the next states?
So,
Can you repeat the question?
the question was, how many steps ahead do we look? We look 1 step ahead. It's already enough. No. There are certain methods in reinforcement learning where you look multiple steps ahead. So tomorrow in deep Q learning, we're going to look n steps ahead. But here, we're going to look 1 step ahead.
Next week.
Next week.
Tomorrow.
Oh, yeah, next week, sorry.
Don't come here tomorrow. We're not serving pizza.
Quick question. So the reward seems to be the same. The reward is the same, and that means one is not better than the other in the states.
Future reward.
No,
immediate reward.
This is the R. This is the reward, right? And this is gamma of my future discount times the next state, right? So here this R is 10, both, right? But here the one value function has minus 100 because you die. And the other one, the value function has say 0 or another plus 10 because you move more frames to your right. And of course this will become the more favorable state and has a better value function. The value function estimates how good my state are. The value function of the state. Yes.
So just one question is for it to know the value of future states as it goes through multiple loops. Would that be a better understanding of the environment?
Exactly. So it's going to loop the different approaches. So you can say I'm going to do like a Monte Carlo approach, right? I just play infinite games and I just average my future rewards from that state, right? Or we're gonna, but this is very slow and very inefficient. So we're gonna talk a bit about dynamic programming, and then we see like how much time we have for the Monte Carlo and the Q-learning. Yes.
So when this entire process begins, it doesn't know what the future states are, correct? Like it doesn't understand that there is potential additional route you can take and what the reward for that will be.
Yes and no. So you want to do the dynamic programming, initialize a whole state action matrix. So the model has kind of a memory for the whole state and action pairs.
To identify the entire
Say
environment.
you do deep Q learning, it doesn't have, like, it kind of does a neural network. So you put the state in and kind of neural network going to process it, information, and gives you something out. But it doesn't, what you do, you play games, you generate episodes. And then in these episodes, in these like atomic steps, these single steps, you know the next state. But say for deep, gonna take a little bit ahead. So you see here for the dynamic programming, you also need to know the probabilities of all your next steps, all the probability and transitions, and also So you need to know the next step, right? And for some models or for some games, it's going to be explosion, combinatorial explosion. So that's the limitation of the dynamic programming. So guess we're done now, right? We just find the best value functions. Well, we need to make sure that we have like such an agent would never learn the optimal policy automatically. And even if we have a perfect model, like I said, the search space is going to be way too long because I have my current state, my action, and all my next state spaces. So, and what we're going to do in deep dynamic programming, like we don't necessarily have to do all the states, right? So we do better in frequent state and do worse in less frequent states. And what we're going to do, we're going to use some value functions to perform a structured search for good policies. And it's this kind of an iterative approach. So we have a value function, v1, and we just use the Bellman equation to update the rule. We just keep updating it. So, and we kind of replace like the old function with the new function. And we stop updating when we observe like minimal change. I can show you a little bit. See if this runs on this machine. So this is like called reinforced JS. So it has some and this does some kind of value iteration. So it just kind of starts and then it goes through all the states and then it just updates. And this is what the dynamic programming algorithm looks like. So what we're going to do, we're going to go through all the possible states. We loop through all the states. And we kind of say, okay, the v is the value function of that state. And we say, okay, the updated value state is like the maximum action, like the maximum score we get for the probability given all the future states, right? And we say delta is like the difference, like how much did we update the v. And if it's small, we just stop. And in the end, we create a deterministic policy by just taking a greedy maximum over all the value functions for each state. For all the actions, like we calculate which action gives me the best next state. So we're going to loop through all the states. We just initialize state with random values, and we just do it for all the states, and we're going to loop through all the states and each time updated it. And for people who want to know what is like on policy or off policy, so would be off policy because we just select the maximum action for each. So we don't really look into our policy to determine, like we don't even have a policy here. So we don't look in our policy which action to select. So you just say, okay, you just say the value state, the next value state is just the action that gives me the best future state. For this, I have to go through all the actions and all the future states, and then we say, okay, select the best one.
So this is basically the two phases part of the general iterative process of evaluation and update.
Yeah, so we're gonna evaluate here, go all the evaluation, and then we update the value function of the state, and we just do it like iteratively over and over again. We just loop forever through all the states. And we estimate the state, and then we say, okay, we update the state function, and then we say, okay, what's the difference between those two? Is there any questions?
How will this be different from just running all, like, all infinite possibilities, and then just averaging them, once you're done?
It's essentially what more or less we're doing, right? We're summing up over all future states. Like we select the action, right? And we sum up for the maximum action. We sum up all the possible ones, right? And we just do a weighted from the reward plus like what we had in the previous one, right? So it is kind of like just running infinite simulate runs and then just average it over and over.
So, but in your case, you're basically only running those that are likely, or?
So here we run through all each of the states.
Oh, okay.
Just like a double for loop, right?
Yeah, it's a double for loop.
Double for loop.
And we know the transition function.
Yeah, we know the transition function. So if there are no more questions, we're gonna code the dynamic programming algorithm together. Or whatever your preference is, either you can try to code it yourself. We have like some parts missing again.
From online.
Yes.
A question from online says, are the probabilities assumed already known, or are they estimated based on history of results?
The probabilities are already known. Perfect. You mean the probability of the next state and reward, right? This PRSR, right? Okay.